Let us discuss about bounded motion in the surrounding of a planet and escape velocity. So we talk about a planet and say which is having a mass mp and its radius is rp, and say we place a body on the surface of planet say which is of mass m. Here we find out the potential energy of body on surface of planet, then potential energy can be given as minus GMPM over RP. We already discussed in the section of field theory that this negative sign implies attractive forces, or whenever forces are attractive in a system, potential energy of system is always negative, or this negative sign shows us boundness, or it gives us the idea about boundness of this body, or whenever a body is having negative potential energy in the field of another body, it must be bounded with the other body. Now say if we throw the body with a speed v away from the planet, then it will move up, and obviously due to gravity it will be retarded, and at some point at a height its final speed becomes 0 and then it will fall back again. Now in this situation we can say if some energy is supplied, if we can say some kinetic energy is imparted to the body, then the total energy of body will be half mv square, which is the kinetic energy, minus the potential energy is gmpm by rp. So this is the total energy of body on the surface of planet. Now if this energy is less than 0, that means even after supplying some kinetic energy, the total energy is negative. That means at the topmost point of its motion, when its kinetic energy becomes 0, we can write the total energy is transformed to potential energy of body, which is still negative because the total energy is less than 0. So it again shows boundness. That means it is under the influence of attractive forces of the planet and it will fall back onto the surface of planet. But if somehow we can say we supply kinetic energy up to the level that its total energy will be more than or equal to 0, then we can say when it will come to rest, its total energy will transform into potential energy, which will become 0 or positive. That means it will be free from the attractive forces. Then only we can say that potential energy will not hold or it will be 0. So here we can say if a body is projected such that on surface of planet its total energy becomes 0, this implies finally the body will be able to overcome the gravitational forces of planet and it will escape. Let's mathematically analyze the situation on next slide. Here we can state that if body is projected at a speed v such that its total energy, which is half mv square minus gmpm over rp, will be equal to 0, then we can state here m gets cancelled out and the value of speed we are getting is root of 2 gmp over rp. This we can simply state as escape velocity on surface of planet. That means this is the velocity with which when a body is projected, it will not return to the planet, but if it is less than that, it will come back to the surface. Like for Earth, if we calculate We can take its mass me and radius re. So here escape velocity for Earth we can write that this v is root of 2g me over re. And we know well that gravitational field on surface is written as g me over re square, of which the numerical value is 9.8 meter per second square. Here gme by re square, if we substitute it here, this escape velocity can be written as root of 2 gs re. And on substituting the values, this will come out to be approximately 11.2 kilometers per second. This is also a useful result to be kept in mind. With this or more than this speed, when a body is thrown from Earth's surface, it will not return on Earth. The reason is if a speed is this or more than this, the total energy of body will become either 0 or more than 0. And always remember one more point that here in this calculation we have kept planet at rest. So we can say as planet is taken at rest in this calculation, the escape velocity does not depend on direction of projection. Obviously, if we consider the rotation of planet in account, then in the direction of rotation, if we throw the body, we need to throw it with relatively less speed so that the planet speed will be added in it and net speed required will be less compared to this. And if we throw the body in opposite direction, it will be slightly more. So be careful about the calculation of escape velocity for any planet. If it is taken at rest, it can be directly given as root 2g re, or if not, then it will be calculated with respect to planet and correspondingly calculations will be executed.